Hello everyone, I am Dr. Sirajul Faizi. I welcome you in my YouTube channel. Today in this video, I am going to talk about preparations of aldehyde. So let us start learning of reactions of electrophilic additions, nucleophilic additions, free radical reactions, orientation, reactivity and reactions. So let us start addition to carbon-carbon multiple bond. Addition to carbon-carbon multiple bond. What does it mean? It means the breaking of carbon-carbon multiple bonds. Why multiple bond? You know the multiple bond means double bond and triple bond, alkyne and alkene. So how many types of reaction possible at carbon-carbon multiple bond? So first electrophilic additions, nucleophilic additions, free radical reactions, orientations, reactivity and reactions. Another topic which I will cover in this video, addition to carbon heterobonds. Addition to carbon heterobonds means again double bond or triple bond. Addition to carbon-carbon double bond, so carbon-nitrogen double bond here. Addition to carbon triple bond nitrogen, addition to carbon double bond oxygen, addition to carbon double bond sulfur. So first topic I will cover addition to carbon-carbon multiple bond. Then I will discuss about addition to carbon hetero bonds. This is also a multiple bond, either double bond or triple bond. Now addition to carbon-carbon multiple bonds, electrophilic, nucleophilic, free radical. Electrophilic additions, because you know breaking of double bond to single bond, this is the addition. If it is happened with the electrophile, then it is called electrophilic additions. Look at here, step 1, electrophile approaching one carbon, and in step 2, carbocation approaching nucleophile, W minus or base, it is forming Y on one carbon and W on another carbon. So breaking a double bond to single bond through electrophile. Now electrophile can be positive ion, the positive end of the dipole, or an induced dipole with the negative part breaking off either during the first step or shortly after. Look at here, formation of bromonium. So there are three possibilities. Both Y and W may enter from the same side of the plane, in which case the addition is stereospecific and seen. They may enter from opposite side of the stereospecific anti-addition. The reaction may be non-stereospecific. So stereospecificity, this topic is very important for NET examinations. On double bond, reactant, addition and products. Cis, syn, erythro. Cis, anti, thereo. Trans, syn, thereo. Trans, anti, erythro. Remember, cis, reactant, addition, syn, then you will get erythro. Cis, anti, then thereo. Trans, syn, thereo. Trans, anti, erythro. So syn, erythro, trans, anti, erythro, cis, anti and trans, syn is thereo. Or triple bond, syn gives cis olefin, anti gives trans olefin. It is very important for for objective questions, multiple choice questions. Now reaction seen same side, you can see erythro DL pair, NT3O DL pair. Now nucleophilic additions, you can see starting with the Y minus. Now free radical additions, YW breaking Y radicals and W radicals. Y radical initiate the reactions and then you can see the terminate. Now reactivity, electrophilic additions, electron donating groups increase the reactivity of a double bonds toward the electrophilic additions. Electron withdrawing groups decrease reactivity. The reactivity towards electrophilic additions of a group of alkene increase in the order. Look at here, CCl3 CH double bond CH2 less than Cl2 CH double bond CH2 and so on. Now nucleophilic addition, the situation is reverse. So some important facts: comparison between double and triple bonds. There is a higher concentration of electron between the carbon of the triple bond than in the double bond, and yet triple bonds are less subject to attack at an electrophilic site and more subject to nucleophilic attack than double bonds. And this statement is not universally true, but it does hold in most cases. In compounds containing both double and triple bonds, non-conjugated bromine and electrophilic reagents always add to the double bonds. In fact, all reagents that form bridge intermediate react faster with double than with the triple bonds. Now, what is the explanations? The explanation of this fact, as mentioned, it is true that general triple bonds are more susceptible to nucleophilic and less to attack on an electrophilic site than double bonds, in spite of their higher electron density, because the electrons in the triple bonds are held more tightly because of smaller carbon-carbon distance. It is thus harder for an attack electrophile to pull out a pair. The availability of the unfilled orbital in the alkyne. So these are very important facts regarding double bond and triple bond. So you have to look at the reaction site. Now orientations. You know that for electrophilic attack, answer is given by Markovnikov's rule. The positive portions of the reagent goes to the side of the double or triple bond that has more hydrogens. Why does Y plus add to give the more stable carbocation, as in the similar case of electrophilic aromatic substitution? We invoke the Hammond postulate. Say that lower energy carbocation is proceed by lower energy transition state. So for looking the orientation, you have to remember Markovnikov's rule. Now stereochemical and orientation. In addition to an unsymmetrical cyclic alkene, the two groups can come in from the more or from the less hindered face of the double bond. The rule is that syn addition is usually, although not always, from the less hindered face. For example, epoxidation of 4-methyl cyclopentene gives 76% additions from the less hindered and 24% from the more hindered face. So look at here, you have the double bond here, you have the epoxide formations, so 76% and 24%. So reactions, addition of HCl, look at here, formation of 2-chloro-2-dimethyl butane. You can see the mechanisms, how double bond approaching H and Cl minus. You can see how it is attacking on carbocation. So slow or rate determining step is the protonation of alkene to form carbocation. The reaction will take the lowest energy core at this stage. The most stable carbocation will form by rearrangement, and this determines the reduced selectivity of the reaction. You can see the tertiary. So rearrangement via hydride shift or methyl shift. You can see the how hydride shift for the stability and methyl shifts. So rearrangement to form stable carbocations. You can see their rearrangement and different product. Addition according to Markovnikov's rule. You have already know the rules. You can apply it here. So addition to HBr by free radical mechanism, anti-Markovnikov's rule. You can see the product. So adding water across the double bond. You can see. So in presence of a strong acid, polymerization product is obtained. Look at here this mechanism. Now hydroborations. Hydroboration is also very important part for breaking of double bonds. Look at here the mechanisms. So addition of Br2 product from analogous to HBr additions. If you see, you can see the product. You can see the product. Addition to alkyne. Now addition to carbon-carbon heteromultiple double bonds or triple bonds. So look at here carbon-nitrogen bonds and carbon-oxygen bond. Now addition to carbon double bond oxygens. You have this. Now you can see the product situations in step 2. Who attack first? Always nucleophile attack first. In some cases electrophile may attack, but rate determining step is always addition of nucleophile. How they will attack? If a beta positions electron withdrawing group is present, seen. If beta position electron releasing group is present, NT. Now reactivity. Base by donating its electron to the nucleophile make it more powerful nucleophile to attack on carbon. Acid increase positive charge on carbon, increase its reactivity toward nucleophiles. You can see here the formations of 4 bonds means tetrahedral. So A and B electron donating decrease activity. A and B electron withdrawing increase activity. Conjugated increase activity. Steric hindrance decrease activity. Aromatic aldehyde and ketones are more reactive than the aliphatic aldehyde and ketones. So look at here reactions from acid catalyze and base catalyze. Now decrease the stability, increase the stability. Hydrate of chloride are stable. You can see carbon contain 2H group. Now addition of water to carbon nitrogen double bonds. Now hydrolysis of aliphatic nitro compounds, nitrogen. You know they increase the yield at titanium trichloride and activated dry silica gel. Now attack by OR or SR, addition of ROH or RSH. Hydrolysis of nitriles. You have to focus on this type of topic. Addition of alcohol to aldehyde and ketones. You can see diol and diether and go through the mechanism. Now you can see here addition of alcohol to isocyanate. Alcoholysis of nitriles. Attack by ammonia derivative on carbonyl compound. This is very important reaction, that is Mannich reaction. Mannich reaction consists of an aminoalkylation of an acidic proton placed next to a carbonyl functional groups with formaldehyde and ammonia or any primary or secondary amines. The final product is beta amino carbonyl compound, also known as Mannich base. So look at here step 1, step 2, step 3, step 4. So step 1 formation formaldehyde amine, it give amine, and then ketone enol form, then enol form carbanion, amine form carbocation. Now addition of hydrazine derivative, hydrazone, osazone, pyrazolone, osazone, Beta ketoester give pyrazolone. Now attack by hydroxyl groups. Oxime can be prepared by addition of hydroxylamine to aldehyde or ketone. Look at here. So important maximum rate at pH 4 and have different conditions. Attack by halogen, you can see the product. Attack by organometallic compounds, Grignard reagents, formaldehyde primary alcohol, other aldehyde secondary alcohol, ketone tertiary alcohol. Reformitsky reaction, this is also very important reactions. Alpha haloester, beta hydroxy acid, reactivity increased by activated zinc, zinc silver graphite and zinc ultrasound. Now carbon attack by active hydrogen compound, aldol reactions. So scope of aldol reaction, you know the aldol reaction is also very important. Two same aldehyde with alpha hydrogen, two same ketone with alpha hydrogen, two different aldehyde, one may not have alpha hydrogen, two different ketones, one aldehyde and one ketone feasible if aldehyde has no alpha hydrogen, aldehyde also having alpha hydrogen, only alpha carbon of the ketone will add to the carbonyl carbon of aldehyde. So Novelgel reaction. Novelgel reaction is also very important. The condensation of aldehyde ZCH2Z prime, ZCHRZ prime containing an hydrogen with compounds this. Now Perkin reaction, that is also very important. The condensation of aromatic aldehyde with anhydride called the Perkin reactions. You know the base is generally the salt of acid corresponding to the acid anhydride. Alpha hydroxy never isolate, always dehydrated to form alpha beta unsaturated compound. When the anhydride contains only one active methylene hydrogen, then hydroxy compound can be isolated. So look at the aldehyde, you look at the anhydride, how in the presence of RCH2COOH it is giving this unsaturated compound. Now Tollens reagent, that is also very important. In Tollens reaction, the aldehyde or ketone containing an alpha hydrogen is treated with the formaldehyde in the presence of calcium hydroxide in similar base. So look at here. Benzoin condensation is also very important. Addition to carbon sulfur double bonds. You know the sulfonyl chloride can be hydrolyzed, basic catalyzed and usually RO bond cleavage. So my friends, I hope this video will be helpful to you. If you like this video, then subscribe my channel and thanks for watching.